And today's presentation features a project from the University of Wisconsin-Madison, and I'm pleased to welcome our presenter, Boris Claros. Boris, I'll hand it over to you.
Well, thank you, Jacob. Well, today I will be presenting the research project that we conducted at the University of Wisconsin-Madison. And the topic of the research is essentially looking at left turn gap acceptance at signalized intersections with the focus of large vehicles. So to begin with, when we talk about left turn gap acceptance, we are talking about, the driver's decision to make a left turn maneuver when judging different gaps in the opposing traffic. So usually this behavior occurs when there is a permissive left turn signal. And, the driver makes a decision whether it's safe or not based on, different elements in opposing traffic and other, geometric and operational elements of the intersection. For instance, there might be some right turn in traffic while the vehicle is waiting the permissive signal. Also, there might be some pedestrians and cyclists in the trajectory of the left turn vehicle. Also, there might be some obstruction of line of sight, specifically from the opposing left turn vehicle that could be obstructing the side of view of the left turn vehicle and not being able to judge approaching opposing traffic. So there are different elements that might influence left turn gap acceptance behavior, like time of the day as well. And also populations, we've seen some differences with regions within the United States that gap acceptance, specifically left turn gap acceptance, is different across the nation. And we need to consider this type of behavior in terms of driving behavior of gap acceptance. That is very important in the estimation of capacity and signal optimization. So we essentially rely on gap acceptance theory to come up with these estimates. So when we talk about capacity and signal optimization, we talk about the saturation flow. So the saturation flow is essentially the maximum number of left turn vehicles that can be accommodated during the permissive phase. And the HCM essentially provides the base saturation flow with the following equation, in which the saturation flow is expressed in vehicles per hour per lane. And it's a function of the opposing traffic flow rate in vehicles per hour. I should mention that the opposing traffic flow rate, it's considered or it's assumed to be uniform, and there's no randomness or variation in this aspect. So that's one of the limitations of the approach. And also another limitation of the approach is that there are fixed estimates like the critical headway and the follow-up headway, which are part of the saturation flow equation. In this case, the critical headway is 4.5 seconds and the follow-up headway is 2.5 seconds, which have been used since, I would say, since the 70s. And this has been used for many decades. And we need to consider that this equation of the saturation flow, it's used in the current 2016 HCM manual. And also there are many other applications in which capacity and signal optimization uses this equation with these fixed values. And for instance, I could say Vissim uses this estimates. Also, Synchro uses this fixed 4.5 and 2.5 seconds estimates. So when we see the critical headway, so the critical headway is essentially the minimum time interval between two successive vehicles considered to cross opposing traffic. So essentially, what would be that critical headway or that headway that a driver will feel more comfortable taking, or or the closest to it. So in this case, like I said, it's a fixed value. The follow-up headway. The follow-up headway essentially is the distance between it's not the distance, it's the time between two vehicles in the same queue that are accepting the same gap. Essentially, the follow-up headway is vehicles that are following each other within a specific headway. And essentially, that's the follow-up headway when they take a gap together. And I should mention that the critical headway is now defined as the critical headway. Previously, it was known as the critical gap, but the proper definition would be headway, the critical headway. So the 2016 Highway Capacity Manual essentially has these fixed values for critical and follow-up headways. And like I mentioned before, this data was collected from field data in Texas in the 1970s. And essentially there were 3 intersections that data was collected from to estimate the critical headway. And there were 5 intersections that were considered to estimate the follow-up headway. This was long time ago in which they used, camcorders and they did some manual processing and all this process. So the accuracy of the estimates to this time are not considered to be accurate or need to be updated. So unfortunately, these estimates do not account for the geometric and operational measures, at the intersections. Also, the saturation flow doesn't really reflect any variation within these variables. And although the HCM includes some factors to correct or adjust the base saturation flow rate, like for instance, they adjust for heavy vehicles, they adjust for parking plus blockage, area type, lane utilization, presence of cyclists and pedestrians, spillback or work zones. There isn't really an adjustment for geometry or speed limit, for instance. So that's something that we, as part of the research project, set up to look for in the research of this project. So for instance, we evaluated more recent data across the United States from different regions. We quantified the effect of some of these geometric and operational variables that are within the intersections. And we focused on looking at the effect of large vehicles within the data that we found. So the data collection consisted of collecting video data from different locations, and essentially the video recording focused on the left turn maneuvers, opposing traffic, and essentially to be able to visualize the traffic signal indication. We were fortunate to collect around 500 hours of video data from 27 intersections between 2016 and 2019 from Arizona, Florida, North Carolina, Virginia, and Wisconsin. And this data was obtained essentially from projects that were conducted in the area, or we personally, for instance, in Wisconsin, we went to the field and collected the field data for some of these intersections. So with all this data, I know it might seem easy to process 500 hours of data, but unfortunately, it's unrealistic to have one student or one researcher going through all these video when we don't really need that much information from each of the approaches. So the focus was to collect at least 50 to 100 observations per intersection approach. So essentially we were able to collect 100, or we were able to process 147 hours of video, and which resulted in 2,580 observations. And this was around 45 intersection approaches. So in the image, we can see that we used 2 cameras from 2 different angles that allowed us to capture the left turn vehicle, the queue of the left turn vehicle as well, and opposing traffic and the signals. So that was the primary goal of the data collection, to be able to visualize this, so that will contribute to the data reduction. And what we collected when we did the data reduction was essentially collecting timestamps. So the timestamps were essentially collected when the left turn vehicle arrived at the stop bar and when the left turn vehicle crossed over the opposing traffic lanes. And in terms of the opposing traffic, we collected timestamps of opposing vehicles that arrived at the stop bar. So every single vehicle that crossed the stop bar of opposing traffic, we recorded that timestamp. And we can see a schematic of that process. So for instance, we can see in time 3, the left turn vehicle arrival timestamp. And then we can see in time 5, for instance, when the vehicle crosses over the opposing traffic lane. So essentially, those are the 2 timestamps that we collected for the left turn vehicle. And we can see in the other timestamps, for instance, every single vehicle that crosses the stop bar in the opposing traffic, that timestamp is recorded as well. So these timestamps essentially help us to determine, the gaps, the headways between vehicles, and also which headway did the left turn vehicle rejected and accepted. So in terms of the methodology, we use the mean critical headway, which was estimated using the maximum likelihood method proposed by Troutbeck, which essentially takes into account the largest rejected headway and the accepted headway to estimate the critical headway. So the critical headway essentially is greater than the largest rejected headway, and it is smaller than the accepted headway. And the probability of the driver's critical headway is the difference between the cumulative distribution functions. And essentially through maximum likelihood, we can maximize the probability distribution of all these drivers and get a maxima or a maximum estimate, which will be essentially the mean critical headway with the corresponding standard error. So that's for the critical headway. Then we have the mean follow-up headway, which we were very careful to select vehicles to estimate the follow-up headway because we only included vehicles that were in a queue and vehicles that had a lead queue vehicle that took a headway instead of a lag, because when vehicles took lags, those vehicles essentially did not reject any headway and usually did not stop at the stop bar to look for acceptable gaps. So also we did not consider vehicles that shortcut the trajectory of the lead vehicle. For instance, we observed that there were some following vehicles that actually turn in parallel to the lead vehicle, so they shortcut the trajectory and were taking advantage of the time or going in parallel with the lead vehicle to make the left turn. And also we did not consider vehicles that make a left turn during the protected indication or the end of green phase, because those did not really reject a gap, because vehicles by that opposing traffic, essentially by the time that those vehicles make the left turn, opposing traffic was already stopping and not going through. So the calculation of the mean follow-up headway was just essentially obtained using the arithmetic mean and standard error, because there's not really a observable type of distribution than just a normal distribution. So we use those methods essentially to obtain the mean critical headway and the mean follow-up headway. So for each of the 45 intersection approaches. So now we wanted to, try to combine all this information from all these different intersections that have different features and, geometric and operational characteristics. And we use meta-regression analysis essentially to do like a kind of a meta-analysis. So it essentially combines the result from these multiple studies and has it as a function of response predictor variables. So the variables that we explore to put into this equation was the distance of the left turn and opposing traffic stop bar, the left turn offset, the median width, the posted speed limit, waiting time, the width of opposite lanes, and the left turn vehicle type. So which helped us determine, whether this was a large vehicle or not. So we considered large vehicles as, single unit vehicle, buses, and semi-trailers as well. So the results using, the maximum likelihood method, the arithmetic mean for the follow-up headway. So what we can see in the image is essentially a comparison of the HEM estimates and the average of, or I would say the mean of the critical headway, which is 4.87 seconds compared to a 4.5 seconds of the HEM. And we need to consider here large vehicles, right? So we can see here that although we had a limited number of observations that we were able to obtain for large vehicles, essentially we got 18 left turn vehicles from all the data set, which included 2 school buses, 12 single unit trucks, and 4 semi trucks. So the critical headway for those were 6.03 seconds, which is more than 1 second higher than just the mean critical headway with all vehicle types. And we can see that there is a distinct variation around the mean. Not necessarily there's a specific trend with these facilities. And we can see a similar pattern with the mean follow-up head weight of 2.73 seconds compared to a 2.5 seconds of the HEM. So we can see that there's a lot of variability, right? And that the means are not similar to the fixed values of the HCM. So essentially, both of the estimates, the critical headway and follow-up headway, are higher than the HCM estimates. So what happens when there's this difference between the HCM estimates and what we have observed in the field? So the effect is reflected in the saturation flow, in which we can see that, you know, if we input all the extreme values that we've seen from the different intersections, essentially from 45 approaches, is that we have a variation of -30 to 23% difference in saturation flow if we consider, you know, the different characteristics of these intersections from different regions. So these terms essentially are not fixed values, but at least, you know, for the simplicity of the equation, these will provide some saturation flow rates, but unfortunately, these will have some variation depending on the type of intersection that we are analyzing and, you know, the type of gaps that are observed within that intersection. So unfortunately, these differences do influence signal optimization and also the estimation of capacity. So these need to be considered and try to, you know, come up with a more accurate estimate in terms of randomness of opposing traffic volumes and other effects that influence, you know, the saturation flow rate, accounting for the characteristics of these intersections. So what we did is, what we tried to attempt with the meta regression analysis is essentially try to introduce some more predictor variables into the equation to be able to predict the critical headway and follow-up headway based on these variables, excuse me. So we can see that, you know, there is a trend, increasing trend essentially as the speed limit and width of opposing traffic increases, the critical headway and follow-up headway will increase. And this is from a meta regression analysis, right? For instance, each of these dots in the figures will account for sample size and the accuracy of the estimate from each of the intersection approaches. So a meta regression analysis is appropriate for this effect because since the estimates that we have from each of the intersections have a mean and a corresponding standard error, we can account for that variation into the equation and come up with a meta regression analysis. So when we plot the saturation flow in terms of the speed limit and the width of opposing traffic, we can see that, you know, with a decreasing speed limit and width, which will increase the critical headway and follow-up headway, will result in a greater saturation flow rate. And hopefully that association will help a little bit practitioners to determine, you know, the effect of some operational and geometric features in, you know, the estimation of the saturation flow rate. So in conclusion, the mean critical headway and follow-up headway were higher than the fixed 4.5 and 2.5 seconds of the HCM values. And large vehicles critical headway were 6.03 seconds, which is 1 second higher than, you know, the average or the mean 4.87 seconds of the critical headway that we observe with all the data from the 45 intersection approaches that we, you know, across the nation, we collected data from. And essentially, if large vehicles were observed in a higher proportion of traffic in the left turn movement, we expect that that will generate a smaller critical headway and resulting in a lower saturation flow. So the saturation flow essentially has a difference from side to side in terms, you know, of, you know, the value per lane, in which we were able to observe that there was a difference of -30% to +23% in the magnitude of the saturation flow estimate. Also from the meta regression analysis, we were able to observe that with decreasing speed limit and width of opposing traffic, we were able to observe that the smaller critical and follow-up headways will result consequently in a greater saturation flow rate. So from the limitations that we observe in the different aspects that we saw with the data in the data reduction was that there were some instances that we had drivers that were distracted. Some call it erratic drivers in terms of gap acceptance, in which the driver accepted a gap that was larger than the largest rejected gap. So there were some instances that we flagged in which it was not clear why a vehicle did not take a specific gap if it was an acceptable gap. So we also noticed that there were the presence of pedestrians that may have influenced gap acceptance, specifically if they were just waiting on the sidewalk. And also something that we notice is that the effect of the obstruction of line of sight, specifically from opposing vehicles in the opposing left turn movement, especially if there were large vehicles in the opposing left turn lane that prevented the vehicles from seeing the opposing traffic. So those are some of the limitations that we have with the project, and we actually plan to continue this research since we have a vast amount of data that we already process as well. So we plan to continue some efforts into looking into more detail. For instance, we are planning to look at the obstruction part of it. We are planning as well to look into erratic drivers. And we are also planning into looking at the gap acceptance, specifically the critical gap acceptance by the location of opposing traffic. For instance, you may notice that in this study, we just focused on, all vehicles that are going through in the opposing traffic without considering, if they were on the, closest lane to the left turn opposing lane. And so we want to look at, that interval between opposing traffic and the location of the lanes in which they are located. So that's some of the research that we're hoping to conduct. And part of this project was published on TRR, specifically in looking at the critical gap and follow-up headways from all these different intersections. So I think that's all I have, and I really appreciate your attendance and being able to present my research here. Thank you.
Interesting work, Boris.
Thank you.
That's awesome stuff. We will open it up for the Q&A. If anyone does have questions, they can submit it in the chat box. I do see one that was submitted. Was the data collected during COVID time?
No, the data was actually collected from 2016 to 2019. So yeah, we didn't have any data post or during the pandemic. Yeah.
Good question. And I'll follow up with that a little bit. Was that collected year round then? And did you notice any differences maybe during if there was potential weather occurring, whether that be rain, snow?
Yeah, so actually we narrowed down the data collection to daytime in summer periods. For instance, in Virginia and North Carolina, we got some data from. This data was from existing projects. For instance, they collected data from a couple of days, and we were able to get that data from those projects. And if we were able to see, for instance, the signal timing and things like that, we also obtained that data. But yeah, it was during the daytime and summertime.
Excellent, thanks. Okay. Well, while we're waiting on other questions to come in, I will remind everyone that this presentation from Boris will be available online on our YouTube channel and website in the next couple of days, and we will share that link with all of the registrants. So feel free to pass that around to any colleagues that may be interested. I will put in a pitch for our next webinar, which is November 2nd, and that will feature another research project from the University of Wisconsin, Madison. This is also a collaborative project, so the University of Iowa is also involved, and we will be sending that registration info soon. And I'm not seeing any other comments, Boris. if there are any questions, look at the screen. You can see the emails of Dr. Noyce, Boris, and Madhav there. And I will include Boris's email when we send out the recording link as well. So feel free to continue the discussion or any questions with Boris afterwards. And with that, I think we can end it there. Thanks again, Boris, and thank you all for joining, and we will see you at our next presentation. Thanks.
Thank you.